that's basically enough to really understand the production cross-section and the decay width, so the lifetime of the Higgs boson. So again, let's try, first of all, to figure it out how long does the Higgs boson live. Right? I mean, you spend a lot of money, you spend you build big colliders to produce the Higgs boson, but at least you want to know if you have a chance to see it. So what is a lifetime? Right. As I said, it can decay into all particles that are lighter than the Higgs, right? And since the couplings are proportional to the mass, it will couple the most strongly to the heaviest particle it can decay into, which in this case is simply the bottom quark. So you have the Higgs, like this, decaying into a pair of B quark. And that will be the dominant contribution to the decay width. So let's try to compute this partial width of the Higgs into BB bar. Right? So again, using dimensional analysis, right, we know that this has to have the dimension of a mass. Right? And clearly here it will be simply proportional to the coupling squared here. Right? So it will be proportional to GHBB, the coupling of the Higgs to the bottom quark. Right? So what is this coupling? We say that it's proportional to the mass of the B divided by the Higgs expectation value. Right? So what is the dimension, first of all, of this object? Right? So here we have the Lagrangian, that is basically HB bar. Right? If you want to put a bar. Yeah. The bottom quark is a fermion, so he has a mass dimension 3/2. The Higgs is a scalar field, so he has mass dimension 1. So it means that this product of field is mass dimension 4, so the interaction, the coupling, is dimensionless. So here it's just a dimensionless coupling, GHBB. Right? So that's exactly what is happening here. Right? The mass of the bottom quark is mass dimension 1, and the Higgs expectation value, it's a vacuum expectation value of a scalar field, so he has the same mass dimension as a field, so it's mass dimension 1 also. So this is dimensionless. Right? So this is dimensionless. So clearly here, you need, just for the dimension to match, right, you need to add 1 power of a mass, and here the mass that you are at your disposal is the mass of the Higgs boson. Right? I mean, at the end of the day, the mass of the bottom is 4 GeV, so you can neglect the mass of the bottom compared to the mass of the Higgs. And here there is simply a phase space factor. So in this case, for a two-body decay, just 1/8 pi. Right? So you replace this coupling now by the mass divided by the VEV, mass B. Yeah? And you take the square just to, as before. The amplitude is proportional to the coupling, and the decay width is proportional to the coupling squared. So now you put the numbers. So it's 1/8 pi is about 1/10. Right? Mass of the bottom is 4 GeV divided by 125 squared times 125 GeV. Right? And if you haven't done any mistake, this is about 1 MeV, right? Which is 10 to minus 21 second minus 1. Right? So you see, you can easily understand really the basics property of the Higgs if you know its selection rules. The selection rules of the Higgs is that its coupling to the particle are proportional to the mass of the particle. Okay? So now, other exercise. What is the production cross-section of the Higgs at the LHE? Right? So LHE, you're colliding proton. At the end of the day, the proton are, okay, proton is up, down. But at the end of the day, if you take into account the parton distribution function, at high energy, the proton is essentially actually gluon. So what is happening? Well, first of all, also because the up and the down are very tiny coupling to the Higgs, so they basically don't contribute at all to the production cross-section to the Higgs. So the main production mode is actually what we call gluon fusion. So you have the two gluons inside the proton that form virtual top quark, and the top quark has a large coupling to the X. So that's exactly how the X is produced. So let's try to compute the cross-section for this process. Right? So here is QCD. I haven't talked at all about QCD yet. It's part of the standard model, but okay. It's a little bit boring, QCD. But we'll discuss that tomorrow. It's boring because it's non-perturbative, so at least at low energy. At high energy, it's very nice. It's asymptotically free. We'll discuss that tomorrow. It's very nice. But okay, so this is just QCD. So this is G strong, the coupling constant of QCD. And here, again, is the coupling of the X to the top quark. Right? So this is M top divided by V. Okay. What is the dimension of the gauge coupling of QCD? So it's a coupling between the gluon and two quarks. Right? So again, is a vertex of mass dimension 4. Right? 3 half, and spin 1. Well, maybe we didn't discuss the mass dimension of spin 1. It's true, yeah, we didn't. But it's easy, right? It's F mu nu is a kinetic term with a gauge field, right? And d mu, F mu nu is d mu A nu minus blah, blah, blah. So basically here you see that in the Lagrangian you have two gauge field and two derivative. So it's telling you that the mass dimension of a gauge field is 1, right? So here you have 1, 3 half, so it means that the gauge coupling is dimensionless, as it is for QED, as it is for the weak interaction. Okay, so now with that we want to compute the cross-section. So remember that the cross-section has a mass dimension -2, right? It's just an area. So mass to -2, M -2. So it is proportional to GS times GS squared when you're taking the amplitude squared. So it's GS to the 4th. It has to be proportional to the squared of the X coupling to the top. M top divided by V squared. There is also some phase space, which is again 1/8 pi. And then here you have a loop. Every time you have a loop, you need to add this 1/16 pi squared factor. Okay. Just to get the numeric a little bit closer to reality. So really you need to put this loop factor. And now let's try to match the dimension, right? So you want M to -2. Here you have dimension less, dimension less, dimension less. So you need to put a mass to -2. And then what is the mass that you should put? So here you have to think a little bit. Maybe you could put the mass of the X, the mass of the top, the mass of the gluon is 0, so it doesn't matter. At the end of the day, the real answer is actually the mass of the top that you need to put in these diagrams. And again, here you can plug the numbers, right? I mean, you know the mass of the top. M top is 173 GeV. The mass of the, well, V, yeah. I didn't mention at all yet what is the value of V, but okay. It will come. I will tell you, right? V is 246 GeV. And what is the value of the gauge coupling, of the strong gauge coupling is, okay, you can take something of order 1. I mean, it's strong couplings, etc. Okay, so if you put everything together and convert electron volt into whatever centimeter, you will find that this cross-section is actually of the order of 10 picobarn. So from there, you can actually compute how many Higgs boson have been produced by the LHE. Right? I think Laura mentioned that LHE so far has accumulated, maybe I shouldn't use this curly L, has accumulated a luminosity of the order of 100 inverse femtobarn. Right? So it means that the number of Higgs at the LHE, right, is the cross-section times the luminosity. So it's 10 picobarn times 100 inverse femtobarn, and this is about 10 to the 6. Right? So the LHE has produced about 1 million of Higgs boson. Right. Any question here? Yes.
So, is there a way to see again why it is like the top mass to the -2? Because it's like weird to me that it does not depend on the mass of the particle running in the loop. Yet
Well, I mean,
you say that the one that contributes most.
Yeah, no, that's a good question, and because you can ask yourself at the end of the day, you see that the mass of the top dependence cancel out, right? Mt squared divided by mt squared. So you will tell me, yeah, but okay, there is more quarks on the top. You could add the up, the down, the strange, the charm, the bottom. Mm-hmm. So shouldn't the cross section, 6 times larger, or maybe? Mm-hmm. The answer is no, actually, indeed, because that's due to the structure of the loop. So this result is true for quarks that are much heavier, actually, than the Higgs boson. Okay. Otherwise, you can see by computing explicitly the loop that the loop factor goes to 0, basically. It's proportional to the mass divided by the mass of the Higgs, typically. Right. So the only quark that have a sizable contribution is the top. Actually, the bottom has also a small contribution, so it's a correction of the order of few percent to this cross-section. But the other quarks basically don't contribute at all. But indeed, this, you can understand that only if you are computing explicitly the loop.
Okay, thank you.
By the way, this is also a proof, somehow that there is no other quark heavier than the top, right? Because if you have, a fourth generation that gets its mass, fourth chiral generation, so a new quark that gets its mass through the Higgs mechanism, it will be again heavier than the top. So it will also contribute to the production cross-section of the Higgs, and that will be in contradiction with the cross-section that is being measured. So that's fantastic proof, right? You measure the cross-section production of the Higgs, and you learn that basically there is no fourth generation like in the standard model. I mean, there could be some heavier quarks, but the mass of these heavier quarks, won't get all their mass from the Higgs mechanism. So that's why you need to introduce sometimes some vector-like quarks. I mean, some of you, I think, are working on these vector-like quarks. That's not the same object as a top, right?
Yeah, talking about corrections, how does it work here, the perturbative expansion you're using? Because you are saying the strong coupling is of order 1, so it seems that non-perturbative corrections should be applied, right?
Yes, and indeed, I mean, okay, I'm sure that Laura will discuss that in more details. The next two leading orders, so this is a leading order. So yeah, the leading order in this case corresponds to 1 loop. So the next two leading order is 2 loop. People have computed to n cube LO, actually next to leading order. But it turns out that indeed in this case, the corrections are sizable. I mean, there is a K factor more than 2. So it means that the NLO is larger than the leading order by a factor 2, right? But that's not so much due to the fact that G strong is close to 1. It's really due to some phase space issues. There is new diagrams that basically contribute to this process. So it's not really a concern about the validity of perturbation theory. It's more like bread and butter problems of QCD. I mean, you need to look at all possible diagrams, and there are new phenomena that occurs when you go to higher order. So again, there is no worry about perturbation theory. And indeed, I mean, perturbation theory converge in this case. I mean, you can say that n cube LO is a small correction to n squared LO. So everything is under control. But of course, phenomenologically, it does matter because a K factor of 2 or even 2.5, if you want to compare with experimental data, you need to take into account. So that's why people spend so much time on these quantum corrections. Yeah.
So if the principal decay mode of the Higgs is via 2 bottoms, isn't the other way around, 2 bottoms going to a Higgs have a bigger cross-section than that process?
Well, no. I mean, first of all, you need to look at how many bottoms are there into the proton, right? And actually, the PDF for the bottom quark is tiny. So there is more gluon, in a sense, than bottom quark. Okay. So that's why you cannot reverse the process. Okay.
This is the main production channel, the LHC.
At the LHC, yes. at the LHC. I mean, of course, at E plus E minus collider, you don't have gluons, right? I mean, so yeah, maybe I can mention that at E plus E minus, production mode is actually E plus E minus. You are producing a Z boson, and then the Z goes into Z and X. So that's what is called the X stralum. You radiate the X from the Z, and that's the cross-section that has a peak at 240 GeV. So that's why FCC or the linear collider wants to run at 240 or 250 GeV just to produce the X with the highest possible rate. I mean, at the LHC, so I say that that's the dominant mode. That's the one, that has been first observed on the 4th of July, 2012, when Rogerio was at CERN, to cheer us up. But since then, I mean, you have also been able to observe actually subdominant decay mode, vector boson fusion. So again, using the fact that the quark can radiate some W on the Z, and the Z, so something like that. So you have a quark that radiates a W, a quark, another quark. So here it could be a W as a Z, and then you're producing a X, right? So that's another mode, another production mode of the X that has been observed. The cross-section is about 1 order of magnitude smaller than gluon fusion. There is still another one. I mean, okay, you have also similar things to X stralum, right? QQ bar, Z, ZX. So this has also been observed. And then there is another interesting mode, which is TTA, in association production with the top, right? So now, how does it work? Forgot. So the top here. So TTH in association with the top quark, right? So this has been observed also, even though it's there's something weird there. Okay. There is TTH production. I cannot draw the diagram any longer. It's too early in the morning. Okay, sorry. Probably there is a gluon. Yeah, probably you want the gluon, no? Yeah, it's probably better. Okay? T. So all these modes are subdominant. They have a rate which is basically 1 order of magnitude smaller than this one. But LHE has so much luminosity that those modes have been observed. And you know how to distinguish those different modes. I mean, here clearly you will have some extra jets which are coming from this quark that are radiating the W. So you tag your event with additional jet. Actually, those jets are forward, so they are basically in the direction of the beam. In this case, I mean, it's easy. You have additional top. The top decays into W and B, so there is a lot of final state, a lot of hadronic state. And here, again, I mean, you reconstruct the Z very easily. So all these things have been observed and measured, and everything more or less agrees with the standard model, which is good because, all these processes also allow us to reconstruct the coupling of the X to the various particles. Here, you measure the coupling of the X to the top. Here, you measure the coupling of the X to the W and the Z. The same is true here. So you have really access to various coupling of the X by measuring the various mode of the X. Yes, so I mentioned that for the decay, right? So this is a dominant decay mode. Nonetheless, this is something which is very hard to observe, simply because seeing 2 big quarks in a hadron machine is close to impossible because there is a lot of QCD processes that is also producing many big quarks. So you cannot disentangle the signal from the background. So this is not the way the X has been observed. Rather, the mode is actually when the X decays into photon. Right? Because the photon, you can easily see them in your detector. You can easily measure their momentum, their energy. So you can reconstruct, the kinematic and look at the peak, and you have a very nice peak at 125 GeV. So that was really the observation mode of the X. Two? Two gluons, yeah, but the gluon, again, is QCD, so there are many ways to produce gluons. And gluons, you know, I mean, you don't see a gluon, you see a jet. Right? The gluon don't exist as free particles. Sure, right, absolutely, yeah. But yeah, gluon, I mean, the decay fraction into gluon is sizable. I mean, it's larger than the decay fraction into gluon, into photon, but it's much harder to see. There is another decay mode is when actually the X decay into ZZ star. So of course the X cannot decay into 2Z boson because you know the Z is 90 GeV, the X is 125, so you don't have enough energy. Nonetheless, what you observe is the decay into an off-shell Z, and the Z then decays into leptons. Right? So it's just that the invariant mass of the two leptons here won't be 90 GeV, but still is off-shell. Right? So it's LL. So here you have the X decaying into 4 leptons, and that's also something which is relatively easy to reconstruct and measure in your detector, if in particular if you have electron or muons. Right? So that's the two decay mode that have been observed in 2012. The production was gluon fusion, and those two decay modes were measured. Okay? Good. Perfect. So now I can discuss some symmetries of the standard model. You know, I already mentioned yesterday that the longitudinal component of the W and the Z are actually part of the X doublet. So this is a Goldstone equivalence theorem, and I want to discuss that in more details to really identify actually the right symmetries. You know. Because yesterday I mentioned briefly, you know, at the end of the day, if you consider that SU2 cross U1, you take the global limit, so you break SU2 cross U1 down to U1 of electromagnetism, and you do expect 3 Goldstone boson, right? SU2 is dimension 3, U1 is dimension 1, so 3 plus 1 divided by 1 give you 3. So the 3 Goldstone boson. But actually, that's not exactly the global structure of the standard model. There is an additional symmetry, which we call custodial symmetry. And that's an important symmetry, in particular to understand the spectrum of the gauge boson. Right? Because yesterday, I mean, we derived explicitly, you know, the mass spectrum. We computed the mass of the Z. That was 1/4 G squared plus G prime squared times V squared. The mass of the W squared was 1/4 G squared V squared. And I also told you, right, that you need, I mean, at the end of the day, the Z is a mixing of the gauge boson of SU2 and the gauge boson of U1. So you are performing a rotation. There is a mixing, which is called sometimes a weak angle mixing. Right? So you remember that Z mu was something like 1 over square root of G squared plus G prime squared times, now I don't remember, G W mu 3 minus G primes B mu, right? And the photon was just the orthogonal linear combination, right? G prime W mu 3 plus G B mu. Right? So here, clearly, you go from a basis which is W3 and B, you perform a rotation to go into the Z and photon basis, right? So the rotation, there is a mixing angle, cos theta W, the mixing angle which just measures the rotation that you need to perform to go to the mass basis, right? So the Z and the photon are the mass basis. They have eigenstate of the mass matrix. And in this case, the cosine of the mixing angle is just, you can read it here, is just G divided by square root of G squared plus G prime squared, right? So now, look at this expression here. You know, you have the mass of the Z, the mass of the W, the cosine of the theta W. So you can compute what is called the Rohr parameter, which is the ratio of the mass of the W divided by the mass of the Z divided by the cosine squared of theta W, right? So now it's a very complicated computation, and you find 1. Right? I think I haven't made any mistake here. So there is an important theorem in theoretical physics, right, which is telling you that every time after a very long and complicated computation, you find a simple result. So simple result is 0, 1, pi, e. So every time you find a very simple result means that either you have done a mistake or there is a symmetry that explains why the result is simple. And here, indeed, there is a symmetry. And this symmetry is what is called the custodial symmetry. The custodial symmetry is telling you that the global symmetry, or at least of the X potential, is actually larger or bigger than SU2 cross U1. Right? So remember that we constructed the X, as a doublet of SU2, right? So it's a doublet with an hypercharge 1/2, minus 1/2. I don't remember what we found yesterday. And then, okay, I didn't discuss the X potential yet. Oh, shit. So I should mention the X potential. Right? I told you that, the X acquires expectation value, and so we assume that there is a vacuum expectation value for the X. How does it happen? It happens because the X potential has a non-trivial minimum away from the origin. So most precisely, we write in the Lagrangian, we write a potential. It's a scalar field. As we said in the beginning, you can take any function of the scalar field is invariant under Lorentz symmetry. But now you want also to have a potential which is invariant under the gauge symmetry, right? So SU2 cross U1 is a gauge symmetry. And here you can convince easily yourself that these things, right, is invariant under the gauge symmetry, right? Because H modulus squared is just H dagger H, right? So this transforms as a doublet, this transforms as an anti-doublet, so this is singlet. The charge, have opposite charge, H and H dagger, so he has also chargeless under U1 of hypercharge. So this is totally invariant. You take the squared, blah, blah, blah. This is invariant, right? So what is the shape of this X potential? So that's exactly what Kfir was showing you in his lecture. The potential has this shape, right? So this is V of whatever H, at least. This is H. So at 0, here I've normalized everything. In principle, you could add a constant, right? But the constant is a vacuum energy or whatever, this cosmological constant. So here I'm doing particle physics, so the cosmological constant is totally irrelevant. So I put it to 0. Particle physics is insensitive to gravity, right? It's only gravity that is sensitive to this vacuum energy. So I've normalized everything in such a way that the origin is at 0. No, it's not at 0, yeah. Okay, the origin is here. Doesn't matter again because, it's a constant. So the minimum, at least you have two minima, but those two minima are actually degenerate and equivalent to each other. So this is 0 here. But the origin, when H is 0, it's actually corresponding to a local maximum. So the origin is not stable. It's an unstable point of the potential. And clearly the vacuum, is a state of lowest energy. Means that the state will be here at V. H is equal to V, whatever. Right? So that's why there is electric symmetry breaking, simply because the universe decides to go to the vacuum, to the state of lowest energy. So of course, Kfir discussed, the thermal correction. So this is the potential at 0 temperature. There is some thermal correction. The thermal correction are proportional to whatever T squared times H. So at some point at very high temperature, the potential will look like this. Right? So at very high temperature, you're sitting there. and then the universe cool down, and at some point, you will go there. So that's exactly what happened 0.1 nanosecond after the Big Bang. How did that happen? I don't know. I want to know. Right? That's why I want to build a collider to really see to really see that. Okay. Yeah, so X potential, custodial symmetry, yeah. So I told you, yeah, I want this X potential. So that's the more general potential that I can write, which is renormalizable, meaning that it's a function at most of mass dimension 4, right? I mean, h is dimension 1, I have 4 power of h, so it's mass dimension 4. It means that lambda here is dimensionless, is mass to 0. Right. Of course, and that's something that we will do tomorrow. I mean, nobody is telling you that physics should be renormalizable. That's a concept from the 60s, from the 70s, 80s. But now we have grown-up people, we know that physics beyond the standard model exists, and then you parameterize all your uncertainty, something that you don't know about physics beyond the standard model in terms of higher dimensional interactions. So we will write some correction which are higher dimension, H6, whatever, H8, whatever. But for the moment, let's discuss this renormalizable potential. Right? So, so here I've already assumed implicitly, that there is electric symmetry breaking. I mean, that's why I've introduced this minus sign here. Right? So the potential really has this form. Now, I mean, in principle, I could have written something like that, h to the 4th plus, I don't know, m squared, h squared, plus a constant, right? And for the potential to have this form, I want actually m squared to be negative, right? So I want really a tachyonic mass at the origin. This is instability. Right? So if m squared is negative, I put m squared because usually you put m squared, but it can take any sign. I mean, it's not the square of a real number, right? So this, if this thing is negative, then you have electric symmetry breaking, right? So now, sometimes people are saying, well, I mean, why is electric symmetry breaking taking place? Well, because m squared is negative. And then you ask, yeah, but why is m squared negative? Well, because otherwise, there wouldn't be electric symmetry breaking, right? So clearly you have no explanation. You just parameterize what you know, right? There are models that are trying to understand why m squared is negative. I mean, supersymmetry, for instance, offer a nice explanation. You start at high energy with something which is positive, and then you look at the evolution of the renormalization group evolution, and due to the particular mass of the top, actually you end up with something negative. So that's why also people were fascinated at some point by supersymmetry. Oh, you have an explanation why actually electric symmetry breaking is taking place. There are other models like, compositics, etc., that also implement this symmetry breaking dynamically, a little bit like in supraconductivity. Right? Okay, yeah, I'm getting lost in what I wanted to tell you. Let's get back to custodial symmetry. The question now is, what are the symmetry of this potential? Right? So certainly it is invariant under SU2 cross U1. But there is more. The symmetry of this potential is actually larger. Right, okay, let me drop this. There is various ways to see it. There is maybe the pedestrian way. Pedestrian way is just simply write this potential in terms of the component of the X doublet. So h squared, right? What is it? It's simply h plus h plus complex conjugate plus h0 complex conjugate. And now if you're writing h plus, I don't know, yes, you separate the real part and the imaginary part. It will be the real part of h plus squared plus the imaginary part of h plus squared plus the real part of h0 squared plus the imaginary part of h0 squared, right? So here, basically, what do you see? You see a sphere in 4 dimensions, right? It's just a Euclidean sphere in 4 dimensions. Means that this quantity is actually invariant under a SO4 symmetry. Right? SO4 is just a rotation in Euclidean space in 4 dimensions. Right? Clearly, you can perform rotation. You can transform the real part of H plus into its imaginary part, or the real part of H0, or the imaginary part of H0. And since the rotation conserves distances, it won't affect H squared. So here you see that the symmetry of this potential is actually SO4. So now if you know a little bit of group theory, SO4, at least at the level of the algebra, maybe not at the level of the group, but okay, we are physicists, we don't care so much. SO4 is SU2 cross SU2. Right? So here, you see that you recover SU2, which is nothing than the SU2 of the gauge symmetry. But in addition of U1, here you have actually an SU2 symmetry. Of course, SU2 is bigger than U1, right? SU2 is dimension 3, U1 is dimension 1. So that was a pedestrian way to see it. There is another way to see this SO4 symmetry, which is a little bit nicer. And I want to tell you this, to give you all the secret of the universe. The thing is that instead of H, which is a doublet, you want to construct a matrix H, which is I sigma 2 H complex conjugate and H. Right? So now it's a 2 by 2 matrix. Right? H is just a vector. I told you, I mean, that's really a fundamental property of SU2, that the fundamental representation is pseudo-real. So what does it mean? Pseudo-real, it means that the complex conjugate, if you multiply by I sigma 2, has exactly the same transformation property as H. Right? That's something you can easily convince. I mean, write explicitly the transformation property of a doublet under SU2, with these sigma matrices, and you see that this quantity transforms exactly as a doublet. So that's why, you can combine them into a matrix, because they have the same transformation property. And clearly, the SU2 left symmetry, right, is acting on the left of this matrix. So under SU2, this matrix H will transform as U left H. Right? That's the action of SU2 left symmetry. But now it's a 2 by 2 matrix, so you can also perform rotation among the columns, right? So this is just U right dagger. This is SU2 right symmetry. Right. So you have a matrix that transforms as SU2 left cross SU2 right. So now we can try to rewrite this potential in terms of this matrix. Let's, for instance, let's write explicitly this matrix. Right? So sigma 2 is I minus I. Right? So I sigma 2 is minus 1, 1. So this matrix will be H0 complex conjugate minus H plus complex conjugate, H plus H0. Right? And you can say also, you can compute H dagger times H. So it's again a 2 by 2 matrix. Right? Is H0 complex conjugate minus H plus complex conjugate, H plus H0. H0, no, I need to take the dagger of this, right? So if I take the dagger, this is here. This is here, minus, right? Transpose complex conjugate, right? H0 minus H plus dagger, H plus H0, which is what? It is H0, H0 dagger, so it's H0 squared, minus, minus, plus, H plus modulo squared. The off diagonal is H plus H0 complex conjugate plus H0 complex conjugate minus H plus complex conjugate. So this is 0. This is also 0. And here's the second element. Sorry, it's H plus. So it's again H0 plus H plus complex conjugate squared, right? It means that this quantity is actually H modulo squared times the identity 2 by 2, right? So you see that your potential, you can actually rewrite it as lambda divided by 4, the trace of H dagger H minus V squared. Right? And clearly, the trace of H dagger H, is actually invariant both under SU2 left and SU2 right. Right? If you want, you can be a little bit pedantic and write it explicitly. The transformation property of H dagger H will transform as what? As U right, H dagger, U left dagger. So that's the transformation property of H dagger. Then H is U left, H U right. So this is identity. And then the dagger here. And then if you take the trace, clearly you can bring this U right on the other side. And again, this is 1. So clearly the trace of H dagger H goes into itself. Right? So this potential is indeed invariant under SU2 left cross SU2 right. So what I've shown here, this construction, is just to show you explicitly that SO4 is nothing else than SU2 left cross SU2 right. That's the way the physicists would like to see it. For mathematicians, they don't care, they know it. But physicists need to write how things transform. And that's exactly what we see here. So indeed, the X potential is invariant under SU2 cross SU2. So that's the X potential. Now, what is happening in the vacuum? What is the symmetry that remains unbroken in the vacuum? Right? So for the gauge symmetry, we know, right? SU2 cross U1 is broken down to U1 of electromagnetism. But what is happening to the global symmetry of this X potential? Well, I mean, now it's easy, right? In the vacuum, what is the structure of H in the vacuum? So I can erase this. Right? Okay, let me keep this. What is the expression of this 2 by 2 matrix in the vacuum? In the vacuum, H plus is 0. H0 is V, which is real quantity. Right? So it's V divided by square root of 2 times identity. Right? So the vacuum is proportional to identity. And clearly, identity will remain invariant if you use the same transformation, the same SU2 transformation on the left and on the right. If you take U left equal U right, identity is invariant. Right? So it means that the vacuum is actually preserving a symmetry which is SU2, which is a diagonal subgroup. Right? If you take UL equal U right, you have the full SU2. This is a diagonal subgroup of SU2 cross SU2 left cross SU2 right. So at the local of the gauge symmetry, you are breaking SU2 cross U1 down to U1. At the global level, you are breaking SU2 left cross SU2 right down to SU2 diagonal. Right. So, yes. SU2 left cross SU2 right is broken down to SU2 diagonal. Sometimes you say vectorial, diagonal, whatever. It means that you are doing the same thing on the left and on the right. Yes? The diagonal subgroup, I mean, simply means that you are taking U left equal U right. So clearly, identity, identity, if U left is equal to right, you get identity. So identity is invariant under SU2 diagonal. Is it clear? Yeah.
What are the generators of SU2V? I mean, when you break the symmetry like that, you need to use the generators of the bigger group to generate the other group. So what are the generators that you are using?
The generator are always, I mean, for instance, if it's acting on a doublet, there are always a Pauli matrices. But you know, the thing is that we are using the same gauge parameter for SU2 left and SU2 right. So the generator are the same. What matters is the parameter that you are using to, I mean, like the rotation, right? You have the generator, but you have the angle that measures the rotation. So here, what I'm saying here is that I'm using the same angle for the left and on the right.
I see. Okay, great.
Right.
Thank you.
Okay. So that was, I think, important, right? Because that's really the structure of the Goldstone boson. The Goldstone boson are not associated to SU2 cross U1 broken to U1. The Goldstone are associated to SU2 left cross SU2 right down to SU2 diagonal or SU2 vectorial. So it doesn't really matter because the dimension is the same. I mean, dimension of SU2 is 3, dimension of SU2 is 3, 3. So we have 3 plus 3 minus 3, so it's also dimension 3, right? So you expect 3 Goldstone boson exactly like here. But the structure of the interaction are slightly different. So it's really important to really know what would we call the coset space, right? What is the structure of the symmetry breaking to be able to identify the Goldstone, and then once you know the symmetry, you can write the interaction of this Goldstone. By the way, this symmetry structure is exactly the same structure as in QCD, where you have chiral symmetry breaking. If you consider the up and the down, you neglect the heavier quarks. At the beginning, people didn't know that the strange charm exists, so they knew about the up and the down. There is, again, a chiral symmetry. You can perform, a transformation of the left-handed chirality of right-handed chirality, and then the mass term actually break SU2 left cross SU2 right down to SU2 diagonal. So there is the same symmetry structure as in QCD for the Goldstone. Okay, so now I promised yesterday that I will tell you a little bit about the Goldstone equivalence theorem, right? So I really want to tell you in which sense we can really understand the longitudinal component of the W and the Z are the Goldstone boson associated to this coset space. So for that, and that will be also useful a little bit later, let's discuss very briefly this polarization of the spin 1 field. What is this polarization, the polarization vector? And why the longitudinal component are actually so much different than the transverse polarization, at least at high energy, when the gauge field is very boosted, when it carries a lot of energy which is much higher than its mass. Right? So the polarization is simply writing the gauge field in plane wave. So there is epsilon mu, which is the polarization vector, then there is this plane wave, A, K mu, X mu. Right? So K mu is just the momentum vector of the gauge field, and this is really this polarization vector. Epsilon mu is a polarization. So usually, you normalize this polarization vector by requiring that epsilon mu is equal to -1, and you want epsilon mu to be orthogonal to the momentum vector. So orthogonal in the sense of Einstein, right, in 4-dimensional space-time. And then you want to solve basically this equation and figure it out how many polarization vectors actually exist. So we can go into a frame where K mu is just the energy, 0, 0, and K, right? So the vector, the gauge field is propagating in the Z direction with a momentum K and an energy E, right? And clearly the vector is on shell. So you want m squared to be equal to e squared minus k squared, right? That's the on-shell condition. So now, what are the solutions to this condition? Well, you can construct actually two, what we call transverse polarization. So the transverse polarization are polarization vectors that are really orthogonal to the momentum of the gauge field in real space, right? In the three-dimensional space. So for instance, epsilon mu will be 0, 1, 0, 0, or epsilon mu is 0, 0, 1, 0, right? So clearly they satisfied this normalization condition, and they are orthogonal to the direction of propagation. They are orthogonal in the spatial sense. But you also have one longitudinal polarization, where epsilon mu is actually equal to k, 0, 0, e, and you normalize by 1 over m. So let's check that indeed epsilon mu is equal to minus 1. Well, let's do that explicitly. Epsilon mu, it will be 1 over m squared times k squared minus e squared, right? And by the on-shell condition, this is precisely equal to minus 1. And I claim that this vector is also orthogonal to k mu in the four-dimensional space, right? Epsilon mu k mu is equal to what? Is equal to 1 over m. Then you have e times k, 0, 0, 0, 0, minus k times e, right? So this is ek minus ke, which is equal to 0, right? So it's funny, right? Because this guy has a component exactly parallel to the propagation vector in space, but because we are working in four-dimensional space-time, he has a time component, he has an energy, if you want, and this energy is just ensuring that the polarization vector is orthogonal to the four-momentum propagating vector. Right? And here you see, right, that there is a big difference between the transverse polarization and the longitudinal polarization at very high energy. Right? At very high energy, you have some component of this polarization vector that are growing with the energy. Here, this is constant, right? But at high energy, clearly here, you suspect, right, that this guy will become important because he has a component that is really growing with the energy. So he will become really important at very high energy, right? So the claim is that at very high energy, this quantity that really describes this longitudinal polarization is nothing else than the Goldstone boson of this coset space. How can we see that? Well, let's look, for instance, I mean, you can give formal proof in QFT, whatever, but what does it mean physically, right? Let's, for instance, look at the decay of the top quark. Right? The top quark is a heavy, very heavy quark. It will decay. Its most dominant decay mode is into a W, so the top to W and a B, W plus and B. And now you can ask yourself, what is the decay width, to get, or the probability to get a longitudinal polarized W or a transverse polarized W. Right? So this is an interesting process, right? Because the mass of the top is much heavier than the mass of the bottom, is also much heavier, factor 2, than the mass of the W. But I mean, we don't care. We can go into a limit where actually the mass of the top is much, much larger, right? So we look at the structure of this partial wave, and we are particularly interested in the limit where m top is much larger than mw and mb. Right. So that's something you can compute. I did it for you last night. That's why I couldn't wake up this morning. So maybe it's an exercise, right? It's an exercise because I didn't spend some time deriving the Feynman rules, etc. That's what you do in a quantum field theory lecture. You know, when you have 40 or 60 hours, you learn how to put the factor of pi, etc. Okay, so the partial width for the decay of the top into a bottom and longitudinally polarized W. This is G squared divided 64 pi squared, m top squared divided by mw squared times m top minus mw squared 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 divided by m top to the squared, I think. Let's check the dimension. Right? Cube. It's always useful to check the dimension, right, to find some mistake. So this is dimensionless, m to the fourth divided by m cubed. So it's mass dimension 1, which is exactly what you expect from this. Right? Yeah. And let's compare that. I mean, yeah. These things, I mean, here is just the phase space factor. I mean, yeah, here I've already assumed also that m bottom is equal to 0, right? Otherwise, it's a much more complicated expression. In this limit, this is what you get. Right? So of course, I mean, here, if the mass of the W is equal to the mass of the top, you don't have any decay, right? You don't have enough energy, enough space. So that's exactly what you see, that there is a threshold at m top equal mw. So that's why it's proportional to this difference. Right? Okay, top into bottom transverse polarization is the same factor, 64 pi squared. There is a factor 2, mt minus mw squared divided by m top cube. Right? So what we see is that if, in the limit, I mean, close to threshold, when m top is close to the mass of the W, so this is a ratio of order 1. So close to threshold, you know, those two decay widths are equal up to factor 2, and this factor 2 simply means that you have two transverse polarization and only one longitudinal. Right? So close to threshold, at low energy, there is universality. There is no difference between the transverse and the longitudinal polarization, which is something that you can understand, right? Close to threshold, so when E is close to M, this is 1, 1, 1, so everything is more or less equal, right? So close to threshold, at low energy, you have universality. The transverse and the longitudinal polarization behave exactly identically. But what is interesting is when you go to very high energy, when the mass of the top is much larger than the mass of the W, right? Because then you have this enhancement factor. This is a large factor compared to this one. Right? It means that in this case, you know, the transverse polarization become irrelevant. The only important degrees of freedom is actually the longitudinal polarization. And now, I want to claim that in this limit, actually, this is nothing else, actually, than the decay of the top into one of the components of the X field. Right? So, yeah, the way we compute these diagrams is, again, I mean, really looking at top W, B, right? I mean, this is just the kinetic term, the covariant kinetic term that introduces an interaction of the gauge field with the quark. So that's really coming from the kinetic term for the quark in the Lagrangian. So there is no subtleties. But there is another interaction, right, that you are writing in your Lagrangian, which is the top Yukawa interaction that we have written briefly yesterday, and I will comment a little bit later today, if time allows me. So Y top, we say that it's QL H upright or top right, let's say. So here, for the moment, I will neglect, that there are actually 3 generations. So I'm living in a world where the only thing that matters is the 3rd generation. So there is a top left, bottom left bar, right? So we have seen yesterday that if you, replace the X field by its expectation value, this generates the mass of the top, right? So in particular, this contains Y top V divided by square root of 2, top left bar, top right, right? So this is the mass of the top. Right? But now you have also other interactions there, right? I mean, if you keep all the components of this X doublet, you will have, as we have written, 1 plus H over V. So that's usually the interaction with the X boson. But let's keep for a moment, the other component of the X doublet, right? So H plus V plus H0 divided, okay, doesn't matter. Right? So the claim is that, okay, this will be gauged away at the end. They will become the longitudinal component. But let's assume that I don't know yet that they're becoming the longitudinal component. So now we'll actually have an interaction of H plus, top right, and B left, right? Which is, again, the same thing. So it will be B left, the chirality. So here it's a different meaning than this longitudinal polarization. This is just the chirality of the quark. B left, bar, T right, H plus, right? So it means that here I have an interaction which is top, bottom, H plus, right? And this interaction is nothing else than what the mass of the top. So let's see, 3. Probably I need to divide by V also, right? Mass of the top divided by V. So in this parameterization, I have a very simple vertex, top, bottom, scalar field. And here it's easy to compute the decay width that will be associated to this interaction, right? It will be proportional to the vertex here, so proportional to the vertex squared, so MT divided by MW. And then again, by mass dimension, you will say that the decay width of the top into bottom H plus, right, is equal to, what is it equal to? So there is a phase space factor, which is the 64 pi squared, M top divided by V squared divided by M top, right, the mass dimension. And now using the expression of the mass of the W, which is 1/4 V squared times G squared, you see that the G disappears, and basically you recover exactly the same expression. So this thing is exactly equal to the high energy limit, maybe do it in the other way, right? When the mass of the top is much larger than the mass of the W, you see that those two things are equal. So here, probably I haven't paid attention to this factor 4, but yeah, if you put all the numerical factor, it will agree, right? So that's really an example, of the fact that when the W is highly energetic, so why is energetic? Because the mass of the top is very large. It is much larger than the mass of the W. So here, the W will be highly boosted. So in this highly boosted regime, the longitudinal polarization behaves exactly like the ghost tone. Right. Yes? Well, because, as I say here, the transverse polarization, doesn't, it vanishes. I mean, okay. And this one is much more important. Right? In the high top limit, so M top is much larger than MW. this is negligible compared to this. There is only the enhancement factor for the transverse polarization. Yeah, for the longitudinal polarization. Is it clear? So bottom line is that gauge theory, are becoming very simple in the high energy limit because it becomes basically some scalar field, right? It's just some ghost on boson. So once you know the symmetries, everything is become simple. You don't have to worry about gauge fixing, etc. It's just some very simple interaction here. So why I'm spending also so much time discussing this, the physics of this longitudinal polarization? Because it's another way actually to understand why, at the end of the day, we need the Higgs boson. What is really the role of the Higgs boson in the standard model? Why, at the end of the day, I care so much about the Higgs mechanism? Right? Why don't I simply write a mass term for the gauge field? Right? I told you there are people that think that gauge field is just something that exists in the mind of few theoretical physicists. Right? It's not physical. So why do I insist that the Lagrangian has to be invariant under something which is not physical? Well, I mean, part of the answer is that if you write a mass term for the W by hand, without taking care of gauge symmetry, without introducing the Higgs field, you end up with a theory which is mathematically inconsistent. That means that you are losing perturbative unitarity. You have some processes that grows with the energy, the amplitude will become bigger than 1, and you don't know what to do with this theory. So the real role of the Higgs boson, without thinking about gauge symmetry, spontaneous symmetry breaking, the Higgs boson is simply an additional scalar field that you add in your Lagrangian, and its role is to ensure that all the scattering processes remains finite when you go to very high energy. So it's a regulator. It's a regulator of massive spin 1 particle. So that's what we want, the thing that I will cover now. I don't want to see the Higgs as coming from the Higgs mechanism, whatever, electric symmetry breaking. I just want to construct by hand a theory with massive spin 1 particle. So I will write, I will introduce a mass term by hand. I will add an additional scalar field, and we will see that the coupling of the scalar field to the W and to the quark and the lepton have to be exactly the one that were predicted by the construction that we have done yesterday to ensure that all the scattering amplitude remains finite. Right? So in a sense, I'm doing some bootstrap of the Higgs mechanism. The only thing that I'm requiring is that my scattering amplitude remains finite at high energy. I don't, in a sense, I mean, this electric symmetry breaking Higgs mechanism is a nice way, to tell the story, because you have symmetry. Okay, when you're talking about symmetry, you seems important. But really, what matters at the end of the day are the degrees of freedom and the behavior of the scattering amplitude at high energy. That's only what is physical, things that you can measure. Okay. So let's try to do that. Now that we have understood, that at high energy, what matters at the end of the day are the longitudinal component. You can forget about the folklore of this transverse polarization, and we can see how the scattering of this longitudinal polarization behaves when I increase the energy. So now I just imagine that I have built a very energetic collider that can produce some W's. The W's live long enough that I can scatter those W and see what is happening. How many W's will get scattered in this new collider? So my Lagrangian will be, in a sense, the starting Lagrangian, after electric symmetry breaking. So just describing the degrees of freedom that I know are just the mass for the W mu plus, W mu minus, and then I introduce some interaction. So there will be G squared, W plus, W minus. the quartic interaction that we have seen, basically. But I'm not sure if it's really existing. Okay, like G, there is 4 W's, right? And there is also some interaction, as we have seen, that involve 1 power of the gauge coupling times the derivative, so it's 1 derivative and 3 gauge boson. Right? So the vertices here are simply a contact interaction among 4 W's, right? And now that's really what I'm looking at, right? The scattering of these 4 W's. So what is the behavior for this scattering amplitude? So here you have a contact interaction, which is just a number, which is just G squared. Each of the leg, right, each of the leg grows with the energy divided by m. So you expect that the scattering amplitude, now I'm looking at the amplitude, not the cross-section, right? Should be G squared e to the 4 divided by m to the 4th, right? So that's the first problem, right? I mean, okay, now we end up with scattering amplitude that grows with the energy, so you lose perturbative unitarity, or the probability are becoming bigger than 1. So what can happen, of course, is that there is another contribution to this interaction. So depending a little bit of the plus, minus, or 0, you could have different contribution to this, the T channel or the S channel, right? Or the U channel, whatever. So what is the contribution of those processes, of those diagrams? Let's say you have 4 external legs. So the amplitude here is again e to the 4 divided by m to the 4th, right? That's just a polarization vector. You have the propagator of a gauge field. So it's 1 over mw minus e squared. That's the structure of the propagator, with spin 1 particle. And now, what else? I have twice this cubic interaction. So the cubic interaction is g, so g squared. And then the cubic interaction was proportional to the energy, right? It is 1 derivative. So there is 2 extra power of the energy. And you see here, right, that if you have e to the 6 and at very high energy, neglect the mass compared to the energy, so it's e to the 6 divided by e squared, so e to the 4th, and the sign are such that actually there is an exact cancellation of those terms. So now you are very happy, right? You get a cancellation of the scattering amplitude. It looks like indeed the e to the 4 term cancel. You are left with something which is g squared, e squared divided by m squared. When you do the sum, unfortunately now you still have some pieces that are growing like e squared. You can indeed repeat this computation, keeping the subleading contribution. Those pieces won't cancel if you have only gauge field. You need to add an extra ingredient, and this extra ingredient is precisely the Higgs boson. The Higgs boson, so it's another scalar field that you introduce, right? The Higgs. You will couple to the gauge field in a way which is proportional to the mass. And now, how could we see? Yes. So here again, this contribution to the scattering process here, it will be what? It will be the mass squared divided by, let's say, v squared, whatever. E to the 4th for the external leg, and 1 over mass of the Higgs squared minus E squared, right? And of course, mw divided by v will be nothing else than the gauge coupling, right? So here it's g squared. And you can see now, formally you need to put all the numerical factor, but you see that you have actually a cancellation of this with this. So if you add the X field, and provided that you tune the coupling of the X field to the W in a way which is exactly the one predicted by the X mechanism, let's say, you have an exact constellation, and you end up with a scattering amplitude. Now that remains finite, it will be proportional to the mass of the X divided by the mass of the W. Right? So the role of the X is simply to ensure that the scattering processes remains finite at high energy. And you know, it can do that if and only if the coupling of the X to the W is proportional to the mass of the W. Right? So now you understand really why you need the X, right? The X is not there to break the electroweak symmetry. No, the X is just there to ensure the right behavior of the scattering amplitude at high energy. So you can actually repeat and fully derive the standard model interaction by also looking, for instance, at the scattering of two W that are producing two X bosons, for instance. Or the scattering of two W producing two quarks, or two leptons. And you see that in those diagrams, there is also an exchange of the X boson, which is needed to ensure a finite property, finite behavior of the scattering processes at high energy. So for instance, 2W, let me take my notes to avoid any mistakes. Where is it? I don't know. Here it is. 2X boson. Right? I mean, if you remember in the Lagrangian that we have written yesterday, we had indeed a linear interaction of two gauge boson with one X, but we also had two X boson with two X, right? Simply because we had MW squared, W mu plus W mu minus 1 plus H over V squared, right? So here you have one piece that involves one X boson, but also a piece with two X boson. So you have this process, and actually this is growing like E squared also, and this is cancelled by this kind of interaction, right? So the quartic interaction between two X boson and two Ws has to be tuned to be, let's say, the squared of the cubic coupling between two gauge boson and one X. So this we already know, right? This is what we have here to cancel the growth of WW scattering. Here, we see that we need this interaction to ensure that the sum of these two diagrams also remains finite. So we really reconstruct this full squared here. Yes?
Thanks. We are forced to have a Higgs boson or something like that that is going to contribute this way. So we were forced to have symmetry breaking somehow.
Yeah, I mean, you can reformulate everything in terms of symmetry breaking, indeed.
Okay, so
assuming, wait a minute. Assuming, that I really want to extend my theory to very high energy, right? But nobody is telling you that, I want a theory which is valid up to infinity. Maybe at some point, I have strong interaction, I have new physics that occurs, right? So in that case, the coupling can deviate slightly from the standard model, right? Instead of having an exact constellation, you will be left with a residual growth, So I don't know, something like E squared divided by the square root of 1 minus kappa, right? Or kappa squared or whatever, which is the amount of detuning compared to the standard model prediction. So in the standard model, kappa is equal to 1. Well, maybe it goes into the numerator. So 1 minus kappa squared. Right? So there is an exact cancellation in the standard model. So the amplitude remains finite. If you change slightly, if the coupling are not exactly the one predicted by the standard model, but slightly different, then you are left with something which is growing. And this, is valid up to, I don't know, 4 pi or something like that. So this has to be smaller than 4 pi times V. V squared, or whatever. Right? So it means that if the coupling of the X are not exactly the standard model, you have a cutoff. Right? Your theory is valid up to up to a given energy.
Yes, this is exactly the no loss theorem you were talking about yesterday about LST.
Right. So you will discover the X, or you will discover something else.
Thanks.
Okay. And finally, maybe last word, you could also understand the interaction of the X to the quarks on the lepton by looking at this. So WW, producing a W, and then interacting with two quarks, for instance, right? So this is a gauge interaction, right? So this is kinetic term, whatever. The interaction of the photon, well, in this case, the W with the quarks. And what else? You have another diagram, which is this one, the quark, here in the T channel, right? QQ. And this is growing, the sum of these two diagrams grow like E, actually, like a single power of the energy. And this growth is cancelled if you introduce an interaction of the X with a quark, which is proportional to the mass of the quark. So here it's the X. And in this case, there is an exact cancellation, provided that you tune this interaction of the X with the quark in a way which is proportional to the mass of the quark. And then you are done, you're fine, all your scattering amplitude remains finite. So you're happy because now you can think that you have a theory of everything which is valid up to the Planck scale. Of course, this is very unlikely because this theory doesn't explain dark matter, doesn't explain why you have matter, not antimatter, whatever. So you need physics beyond the standard model, for sure. But now the real question is, what is this dumb physics beyond the standard model that we haven't found yet? We need a new collider. Right? Let's go and build FCC. I need you to build FCC. Right? Okay? So let's discuss that tomorrow. Thanks.
Questions?
I'm just curious, historically, what was the starting point for the Higgs mechanism? This thing about the amplitudes at high energy to be finite or given mass to bosons?
I mean, people knew that there were a problem with massive spin one. I mean, Pauli, Pauli was in Princeton, and there were Young and Mills that came with this non-abelian gauge theory. And Pauli said, well, there is no way, you can give a mass to this guy. I mean, it's impossible. It's inconsistent if you give a mass. So he knew that there were a problem. And then Higgs came from a different perspective. I mean, first of all, it's not only Higgs. There were Braut, Anglais, whatever. There are some Russian, because the Russians have always done it first. There are condensed matter people that say, oh, we have understood everything also. Okay, it's not relativistic, but it doesn't matter. But okay, here, all the problem is really relativity, right? So you cannot claim that, the non-relativistic limit is, you have understood everything. No, really the trouble is to find a relativistic description of massive spin one. So Higgs came with this idea of this Higgs potential, etc., of symmetry breaking. So I think it's a mixture. I mean, it's never one single idea. It's really a combination of various things. There were some problems. The problems were known. People came with some solution, and at the end of the day, yes, the solution emerged as a real one. But probably there were many people that have different solutions that are not the one that nature has chosen, and so we are forgetting the other solution, right? Mm-hmm. But
okay, thank you.
Yeah. It's always easier to rewrite history a posteriori, right? That always everything becomes clear.
No more questions?
What is interesting is that history is always cyclic. You come back with the same problem, with the same solution again and again.
So do we need a third collider after the FCC?
Yes, sure.
All right, let's thank Christophe again.
Thanks.
See you later.